Good morning, everyone. This is Animesh Dutta. It's my pleasure to be here today and very welcome from Canada. It is very early in the morning. Today, I'll be talking about from waste to wealth and integrated, tunable, and circular economy approach for bio-waste valorization. Currently, I am serving as a professor and director of Biorenewable Innovation Lab of School of Engineering and University of Guelph. In terms of my education and my relationship with Asian Institute of Technology, I got my master's back in 1998 from Energy Technology, Asian Institute of Technology, as well as I was an assistant professor from 2005 to 2007 of energy program before I moved back to Canada again. Currently, I am the professor and director of Biorenewable Innovation Lab at University of Guelph, and my research interest mainly on clean energy and sustainable energy development, mainly on waste or bio-waste conversion to bioenergy, biofuel, and biochemicals. In terms of my accomplishment, some of those research has been gone to industry, developing an innovative novel technology on waste conversion, as well as heat transfer aspect of this advanced energy system, and hydrothermal carbonization, which will be the main topics to this presentation. Canada is a big country, and University of Guelph located near Toronto, just 1 hour drive from both Niagara Falls and Toronto. And this is one of the institute that's recommended for overall learning and student support, as well as one of the top school in agricultural science. And given the fact that agriculture is most of the important aspect, and university recognize 3 important global issues. One of is global warming or climate change, that's what we're talking today, as well as energy sustainability and food and water security. And it was realized that sustainable biomass can aspect and contribute towards all those 3 aspects. In the terms of biomass conversion, university has decided to start building 2 facility. One is analytical laboratory and one is research pilot plant study facility. As well as university has a facility for plant-based or farm-based energy system accomplishment. So the types of research that Biorenewable Innovation Lab has been conducting is mainly on thermochemical conversion and biochemical conversion processes. And it was realized that waste is a resource. Actually, it's not a waste, just waiting for an opportunity for various conversion. And all those conversion is complement with life cycle analysis as well as cost analysis. So when we talk about the waste and biomass, we realize it is a carbon neutral and especially waste also, and it creates energy security. But the main technical barriers are their low energy and low bulk density, high moisture content, their fiber difficult to grind, and has a high alkali matter. So the research question that come to the point, so how can we produce an industrial grade biocarbon or biomaterials with very low alkali metal, higher heating value, and high grindability chemicals from these low quality bio-waste resources? So the typical solution currently people are using is a torrefaction, which is just simple heating at low temperature, mild pyrolysis, and able to contribute some of those challenges. For example, can produce high density air fuel, no biocontamination, and hydrophobic materials at the end. So what it does actually, it brings back biomass here from the point to, especially in the lignite stage. For example, as can be seen from here, the biomass here, and by removing the oxygen content, one can bring it back to peat or lignite stage. The problem still is that a higher energy demand for the wet biomass, especially if it is has a lot of moisture, because one needs to remove all those moisture from the biomass itself or waste, and that needs a lot of latent heat of energy. Also, lots of biomass often come up with high ash content that has a high potassium and sodium and alkali metal that contribute to the agglomeration, so torrefaction cannot remove it. In that context, hydrothermal carbonization, which is a techniques that biomass is treated in hot compressed air instead of drying, can make a big instant. Especially what it does, instead of heating it and removing, it cooks underwater like as a pressure cooker, and that is separates the solid material from the other part and deposit it as a hydrochar. So the current conversion technology and hydrothermal conversion technology, if we want to differentiate themselves, so in terms of moisture content, because hydrothermal has a positive response because it's quick underwater, and is also able to remove alkali metal by removing the ash content and alkali by leaching it, and also because heat transfer coefficient in water is very high, so cooking is take much faster. And energy intensity is one of the things that need to be investigated. But in terms of operation, conventional system has been operating over the years, so it's pretty easy to use it. However, hydrothermal conversion, where feeding of biomass is against pressure, could be a challenge and needs to investigate. So in terms of energy, if we look into that, this is a recent paper published in Energy Institute, Journal of Energy Institute. As can be seen from here, if we have a continuous hydrothermal carbonization process where you have a heat recovery, so when a biomass or waste have a moisture content of what 22%, and hydrothermal could be an issue, could be positive. This is one of the things that most of the biomass has more than 50% moisture content, so hydrothermal may take a big role in that conversion. So on that context, biocarbon development research leads into development of variety of waste biomass, especially from woody biomass to tomato vines and wet biomass, municipal and agricultural waste, able to produce carbon, which we can call it hydrothermal carbon, and that carbon further graded to biocarbon for soil amendment, biocarbon for heat and power production, and for charcoal in material application, as well as activated carbon for waste water treatment and energy storage. So if you look into that, some of those solutions, we can say that a wide variety of biomass and organic waste can be processed for biocarbon with desired quality. We also have started to see their heating value and energy density, as well as durability. And the red one, as you can see, that HTC at 260 at 5-minute processing time, able to produce a biocarbon with about 26 megajoule and had an energy density of 27 gigajoule per meter cube, which is similar to that of bituminous coal. And also it has a durability of nearly 95%. So this research is published in Applied Energy Journal. So that can show that this carbon has a pretty high potential over torrefaction, as can be seen. It has a much lower heating value and lower energy density. So what it does comparable to this to the chart. So hydrothermal carbonization able to bring back when you have about 260-degree somewhat air bituminous coal, as can be seen from this band carbon diagram. Whereas for torrefaction process, they are still in the peat or lignite stage. So these can conclude that existing coal-based infrastructure can be used for this kind of biomass conversion process. Let's also look into the alkali content within the ash, and it can be seen that most of the alkali metals such as potassium, sodium can be reduced from about 60 to 80% from the parent biomass. So then that is very important aspect. So one can conclude that HTC processing significantly improve fuel quality and properties of agricultural biomass by removing most of the barriers that inhibits its wider application. We look into that, then we produce this hydrothermal carbonization. It also produces this liquid or processed water. Now, what can we do with this processed water? So what we did, we look into the processed water itself and try to characterize it, and we found that it has contained a lot of acetic acid, lubinic acid, and also some sort of organic carbon. And as we know that this kind of wastewater can be pre-processed with anaerobic digestion, wherein anaerobic digestion hydrolysis is one of the main rate limiting steps. So if we are able to integrate this hydrothermal carbonization process water with anaerobic digestion process, then hydrolysis will be enhanced, and then one can expect more gas yield. So the topic is probably hydrothermal processing has the potential to be integrated with anaerobic digestion to enhance gas yield and co-processing of organic waste. So these all leads to development a complete circular economy approach for a farm. So this slide will talk about an example for a farm based, especially on the corn residue, what one can do looking into the circular economy approach. So what we did here, the corn residue first hydrothermally converted, and then the biocarbon has a potential for various applications for CHP power, for example, combined heat and power or heating. And the liquid processed water can be go to anaerobic digestion, produce a biogas, and the leachate can see that has a nutrient recovery of nitrogen, phosphorus, potassium, and sulfur at the percentage shown. So this paper has been published in Energy Journal, and dashboard shows a overall energy recovery of 79%. So based on this approach, an approach is proposed for a community here in Canada, especially when one have this lignocellulose biomass can be used in the hydrothermal reactor and produce the hydrochar. That hydrochar can be used for the combined heat and power. That can be used for remote community or greenhouse application. On the other hand, the liquid water can be used for anaerobic digestion, further produce the biogas for the greenhouse heating or community, and the community will generate the food waste and energy crop that's further can be processed to hydrothermal reactor. So in a way, it can be able to circulate the whole resources, especially for a rural or remote community. Further, we wanted to develop a value from this hydrocarbon. So the example will show that how can we do the high value activated carbon. So what we do here, we use again corn grains that produce the corn wheat distillation fiber, especially in Ontario. Ethanol is a big industry and they produce a lot of corn fiber currently used for animal feeding or some just waste. So we use that as a resource and did a study on hydrothermal carbonization followed by a chemical activation and deactivation. And the research shows that this has a very high value potential, especially produce high value porous thermally stable activated carbon surface area over 1,000 meters square per gram. And that has a pretty high potential, especially for removing heavy metal or water filtration, gas storage, supercapacitor, and many more. And this research is published recently in 29 SES Omega Journal. And we also look into another area of iron and steel industry, because iron and steel industry using a lot of coal and their CO2 emission is one of the highest per unit production of iron and steel. So we try to reduce this. So this work has been with ArcelorMittal Group of Canada. So we look into agricultural biomass, something like raw sewage gas that has a very high ash content. So we first try to torrefy it, but we found that the ash content is actually increased for the torrefaction process from, as can be seen, from 4.45 to 7.12. Then we first introduce the hydrothermal conversion process, and that hydrothermal conversion process reduce the ash content, and the product further converted to active biocarbon through a slow pyrolysis process at a higher temperature, and that able to produce a biocarbon which is similar to the PCI coal that can be seen in terms of carbon, in terms of heating value, and ash is further reduced fairly heavily, because one of the problem with the PCI coal, it cannot tolerate especially iron intensity alkali metal having in the core. So we are able to remove that, and the process shows that initially it's mostly a leaching process, which is a hydrothermal carbonization processing, and able to reduce lots of the alkali, and then further we investigated and with a slow pyrolysis and able to produce a desired quality of biocarbon. Based on that, we propose this scenario, overall approach of closed loop scenario that able to produce PCI coal type quality carbon from the agricultural biomass or any kind of waste biomass that is the highest content, removing all the barriers, and will be able to integrate HTC process with slow pyrolysis, and that able to replace fossil carbon in blast furnace as well as reduce greenhouse emission. So that leads to the technical progression, because we talk about hydrothermal carbonization is a challenging one, because feeding biomass against pressure is a challenge. So what we did, we developed a bench scale, a pilot scale continuous process, and we tried to study the quality of carbon, and we found that even with continuous approach, the carbon quality is better than the batch quality carbon. And based on this concept, we developed a innovative conceptual design, which is under commissioning. It is a 50 kJ per hour hydrothermal carbonization reactor. So in conclusions, we can say that we are able to pre-process greenhouse residues, energy crop residue, municipal green beans processing waste through hydrothermal processing. As can be seen that this is the key hydrothermal carbonization that are able to produce a hydrocell that can be further converted into biocoke or activated carbon for water treatment, or coal for the CHP power, or electrolysis for the battery as energy storage, or can be used as a catalyst biosynthesis for catalytic activity. The liquid can be again converted through anaerobic digestion to produce biogas, and by cleaning can be used for the biomethane, and the digested can be used for the bird fertilizer. So that leads to a kind of leading to zero waste solution. So we can say that hydrothermal carbonation products from low quality agri-food residue can be potential and newer value chain. And with this, I would like to conclude my presentation, and I would like to thank you, my whole BRIL team, and acknowledge the research support that I have received from all those supporting agencies. Now, if you have any question, thank you. I will wait for that. Thank you very much, and have a very good day.